magnet of length 2L. Here, this is the length 2L of pole strength Qm kept in a uniform magnetic field. Here, this is the important point, uniform magnetic field. B vector. Each poles experience the force of magnitude QMB. Force of magnitude QMB, but acts in a opposite direction. Here, act in a opposite direction. Therefore, the net force exerted on the magnet is 0 because both the forces are equal but acting in a opposite direction. So that is why the net force exerted on the magnet is 0. So that there is no translatory motion. These two forces constitute a couple about a midpoint of bar magnet, which will rotate and try to align in the direction of the magnetic field B vector. Next, important, the force experienced by the north pole. The force experienced by the north pole is nothing but Fn vector is equal to Qm B vector. Similarly, the force experienced by the south pole here, Fs vector is equal to minus Qm B vector. Adding these two equations, both the forces are equal but acting in an opposite direction. So what we get? F vector is equal to F1 vector plus Fs vector is equal to 0. The next, this implies that the net force acting on a dipole is 0 but forms a couple which tends to rotate the bar magnet clockwise here in order to align in it along B vector direction. The moment of force or torque experienced by the north and south pole about a point O is tau vector. Already we know the symbol of torque. Tau vector is equal to, this is the point O to N. ON vector into Fn vector plus OS vector into Fs vector. What is the formula for the torque? Torque is nothing but force into perpendicular distance. Here force is Fn vector, perpendicular distance is On vector direction. OS is the distance, perpendicular distance, then force is Fs. So force into perpendicular distance is nothing but torque. So sum of these two poles of vectors, On vector into Fn vector plus Os vector into Fs vector. Here Fn vector is nothing but, already we know the value of Fn vector. Fn vector is nothing but QMB vector. Fs is nothing but minus QMB vector. Here substituting the value, replace this value Fn vector and Fs vector. We obtain On vector into QMB vector plus Os vector into minus QMB vector. By using right hand corkscrew rule, we concluded that total torque is pointing into the paper. Since the magnitude On vector is equal to modulus of On vector is equal to modulus of Os vector. Os vector and On vector, both the value is same because O to N is nothing but L, O to S is nothing but L. So Os modulus of On vector is equal to modulus of Os vector is equal to L. Similarly, QMB vector is equal to minus QMB vector. Both the forces are equal but acting in a opposite direction. Magnitude of total torque about a point O. Now substituting the value, this value, we obtained tau is equal to L into QMB sin theta, because this is the vertical direction. Vertical component is nothing but sin theta. L into QMB sin theta plus L into QMB sin theta. So L plus L, 2L, QMB sin theta, QMB sin theta, 2 QMB sin theta. So 2L into QMB sin theta. Already we know the formula for the magnetic dipole moment. QM into 2L is nothing but PM. So PM is nothing but magnetic dipole. Tau is equal to PM into B sin theta. Very, very important formula for your objective type question or problem question. Tau is equal to PM into B sin theta. In vector notation, tau vector is equal to P vector M, PM vector magnetic field and non-uniform magnetic field from your third lesson, 12th standard physics. First of all, we should know about the definition of uniform magnetic field. This is the 2-mark question. Magnetic field is said to be uniform if it has same magnitude and direction at all the points in a given region. Example, locally, Earth magnetic field is uniform. The magnetic field of Earth has same value over the entire area of your school. Now, this is the uniform magnetic field lines because it has same magnitude and direction. Same magnitude and direction at all the points in a given region. So that is why we called uniform magnetic field. Next, non-uniform magnetic field. Definition is, magnetic field is said to be non-uniform if the magnitude or direction or both varies at all its points. Example, magnetic field of a bar magnet. Here this is the bar magnet. The direction and magnitude or both direction and magnitude may be vary means this is non-uniform magnetic field. Here diagram or figure A denoted direction is constant. The B diagram shows direction is not constant. The third diagram, both the magnitude and the direction are not constant. So, this diagram indicates magnetic field of a bar magnet. Once again, repeat the definition of uniform magnetic field. Magnetic field is said to be uniform. It has same magnitude and direction at all the points in a given region. If suppose non-uniform magnetic field means if the magnitude or direction or both varies at all its points. In a uniform magnetic field, very important 3-mark question from your third lesson, 12th standard physics subject. Here, when a bar magnetic dipole of dipole moment PM vector is held at an angle theta with the direction of a uniform magnetic field. Magnitude of the torque acting on the dipole. Already we know the formula for the torque. Tau B vector is equal to modulus of PM vector modulus of B vector into sin theta. Here, if the dipole is rotated through very small angular displacement d theta, when we rotate this dipole to d theta against the torque tau B at constant angular velocity should be constant, then the work done by an external torque tau external vector for this smaller displacement, here this is smaller displacement, is given by dw because work should be done when the external torque acting or applied on this dipole. dw is equal to tau vector external tau vector into d theta, because already we know the formula for the work done is nothing but force into displacement. Here force is nothing but external torque is considered as a force, displacement is nothing but d theta is the displacement. The next step, the bar magnet has to be moved at a constant angular velocity, which is implies that tau b vector is equal to modulus of tau external vector. Modulus of tau b vector is equal to modulus of tau external vector. What is the formula for dw? dw is nothing but modulus of tau external vector into d theta. So here both the vectors, the torque are equal. External is nothing but magnetic field torque. So dw is equal to, what is the value of tau b vector? Modulus of tm vector modulus of b vector into sin theta. Here substituting this value, dw is equal to pmb sin theta into d theta. Here replace this value, pmb sin theta vector, pmb sin theta into d theta. Total work done in a rotating dipole from theta dash to theta is Now integrate this term. Integration of theta dash to theta, tau d theta is equal to integration of theta dash into theta. What is the value of tau? Tau is nothing but Pm sin B sin theta into d theta. Tau value is nothing but Pm B sin theta into d theta. This term is equal to Pm B into integration of sin theta is nothing but minus cos theta. Here this is a very small error in your textbook. Only we can put minus cos theta. It is not mentioned d theta because this term is integrated. So PMB minus cos theta limits theta dash to theta. So apply this limit, upper limit minus lower limit, we obtain W is equal to minus PM here minus n minus PM B cos upper limit is theta cos theta minus lower limit is cos theta dash. The next step is this work done is stored in the potential energy. Work is nothing but energy. The work done is stored as a potential energy in bar magnet at an angle theta when it is rotated from theta dash to theta, and it is written as U is equal to, this means U, symbol U, it is represent potential energy is equal to minus Pm B cos theta minus cos theta dash. In fact, the equation 3.26 gives the difference in potential energy between the angular positions theta dash and theta. We can choose the reference point theta dash is equal to 90 degree. So the second term in the equation become 0. Why? Because theta is nothing, 90 degree means cos 90 degree 0. So equation becomes 0. U is equal to 0. And the equation 3.26 can be written as U is equal to minus Pm B because cos theta dash is nothing but 90 degree means this term will be 0. Become a 0. Cos 90 degree is nothing but 0. So the equation can be written as U is equal to 1 with this term minus Pm B cos theta. Here the potential energy stored in a bar magnet in a uniform field is given by U is equal to minus Pm vector dot B vector in vector notation. The next step, case 1. If suppose that the theta value is 0 degree means the equation become cos 0 degree is 1. So U is equal to minus Pm B. If suppose theta is equal to 180 degree, that means the dipole which is rotated towards to 180 degree means theta is equal to 180 degree, then equation becomes cos 180 degree is minus 1. Minus and minus plus. So U is equal to plus Pm B. So we can infer from the above two results, the potential energy of the bar magnet is minimum when it is aligned along the external magnetic field. Very, very important point for your objective type question. The potential energy of the bar magnet is minimum when it is aligned along the external magnetic field, and maximum when the bar magnet is aligned anti-parallel to external magnetic field. Once again repeat, the potential energy of the bar magnet is minimum when it is aligned along the external magnetic field, and maximum when the bar magnet is aligned anti-parallel to external magnetic field.